Today's lesson is going to focus on thermochemistry and the concept of heat. Thermochemistry is the study of heat being released or required by chemical reactions. And all chemical reactions, all chemical processes involve heat. So it's either released or it's required in order for these processes to occur. It is part of a branch of chemistry called thermodynamics, which is the study of heat, energy, work, and their interactions. So in chemistry, we can categorize all processes that occur on Earth as either chemical, physical, or nuclear. So we've talked about physical and chemical processes or changes many times over in your previous courses. We're going to just mention nuclear here as well. And all of these changes, all of these processes either release or require energy. There are also three ways that matter stores energy. And one is in kinetic energy. So we are aware, based on the particle theory of matter, that all particles, all atoms are in constant motion. So they either have translational motion if they're a gas, rotational motion if they are a liquid, and vibrational motion if they are a solid, and also if they are a liquid. Liquids will vibrate a little bit as well. All matter stores energy in the form of potential energy in their chemical bonds. So when the electrons are being transferred or shared and a chemical bond occurs, there's energy stored there and can be released or absorbed depending on whether you're breaking or forming bonds. And then there's nuclear energy. And so this is energy stored in the nucleus that actually holds it together to make it a stable atom. Let's talk about the three changes of matter in a little bit more detail related to energy. So we've heard of physical changes. Physical changes are when we have typically a change of state, and they require small energy changes that involve changes in intermolecular bonds. Okay, so this means intermolecular means between. So these are attractions or bonds between molecules, usually just as they simply change their state. So we can either go from a solid or a liquid or a gas and interchange them. We can also create solutions, which is the aqueous state. And physical changes have the smallest amount of energy. Okay, so make sure you're aware of that. Chemical changes have medium or moderate energy changes. And this is when we now have changes of intramolecular bonds. So this is when we're actually breaking bonds between elements and we're creating new products. Okay, so new products. We're trying to form new products, new substances as a result. So this is when we have, combustion reaction or a neutralization reaction or formation or synthesis reaction. These are the types of reactions you've normally studied in chemistry. And then there are nuclear changes. And nuclear changes is when the nucleus of your element is being altered. And this is not common. It's actually rare to have it happen, but it does happen. We know this with nuclear energy, nuclear changes, fusion, fission. So they have enormous changes based on this nuclear binding energy that holds the nucleus of an atom together. And this is when you have like radioactive elements, not all isotopes of an element are radioactive. So for example, uranium will undergo fission, okay, a certain isotope of uranium where it will break down or decay and the nucleus changes and it creates different elements as a result. These types of nuclear, either nuclear fission, so the breaking down of an atom, or nuclear fusion where we have two atoms, fusing together like in the sun, right? Four hydrogen atoms fusing into helium, release or absorb huge amounts of energy. So what is energy? Okay, energy is actually kind of a hard concept to describe and sometimes a hard concept to understand as well. It is the ability possessed by matter to do work or exchange heat. Okay, so that's your definition of it. And what's difficult about energy is that it's not one thing. It is converted constantly in our lives and in our day-to-day lives. So here are some examples where light energy can be converted into chemical energy. Okay, so the energy that we obtain when we eat a carrot. Electrical energy can be converted into thermal energy, and so on. There are two main types of energy. And the first type is kinetic energy. And this is the energy of motion. Okay, so this is where we would talk about particles moving and moving in different ways. So you can think of like, this person riding on the bike right here, actual literal motion. It could be electrical energy where we have the atoms in our filament right here vibrating and moving around, and then it releases energy as a result of that. There's sound energy, radiant energy, thermal energy. These are all examples of kinetic energy. Then there's potential energy, and potential energy is the energy stored in the bonds of our elements and compounds and substances. And in a chemical form, that's what we're talking about right here in chemical energy and nuclear energy. But there's other forms of potential energy, such as gravitational potential energy, electric potential energy, elastic energy, and that's more in the physics subject area. For us, we're going to be focusing here on these two. And then over here, we're going to be talking about motion, energy, and thermal in terms of kinetic related to chemistry. So we know that energy is the ability of matter to do work. But what is heat? And a lot of people have a misconception about what the term heat actually means. Heat, which is denoted by the symbol Q, lowercase q, is the transfer of thermal energy from one object to another because they are at different temperatures. Okay, so this is the definition. It's the transfer of thermal energy from one object to another because they are at different temperatures. And one thing that you need to know is that heat always flows from whichever object is at a higher temperature to one that is lower. Okay, so think about opening the fridge door at home. There is heat flowing into your refrigerator because it's hotter outside in the kitchen, let's say, than it is inside that fridge. Heat always flows from hot to cold. Objects do not contain heat, but they have energy stored within their chemical structure, right, called chemical potential energy. So we mentioned that in the previous slide, right? For potential energy, we're going to be looking at either nuclear energy or chemical energy. Objects also contain kinetic energies, okay, that move electrons within the atoms, and this is the motion, right? So particle theory, objects or atoms are always in constant motion, and this is where we get our kinetic energies from. Heat is not measurable, okay? You cannot measure heat directly. You measure it indirectly through changes caused by heat. And temperature is not heat. A lot of times students think that taking the temperature of something will tell you how hot or cold it is. Well, that is true, but that is not heat. When you take the temperature of something, you're actually measuring the kinetic energy of that object. So you're measuring how fast or slow the molecules are moving. Molecules or atoms are moving. And the faster that they move, the more kinetic energy they create and your temperature goes up. The slower they move, the less kinetic energy they make and your temperature goes down. So thermal energy is the energy associated with the motion of atoms and or molecules. And thermal energy is a combination of both the kinetic energy, so the motion, how fast your molecules are moving, but it also has to do with the amount of molecules that you have. And it's a combination. Thermal energy can be a combination of both kinetic and potential energies. So, for example, when you exercise, stored chemical energy in your body, okay, which is coming from the food that you eat, will produce the energy of motion and also this thermal energy. So here's a question for you. Which has a higher thermal energy? A cup of coffee at 90 degrees Celsius, so close to boiling, or a bathtub full of water at 25 degrees C? So think about that. Call me over and I'd be happy to check your answer for you. When we learn about thermochemistry, we have to be aware of two terms, and this is the system and then the surroundings. And scientists claim that in thermochemistry, the entire world makes up either a system or the surroundings. So we know that on Earth, Earth is full of matter, and that matter can undergo three different types of changes. We just discussed this. It can undergo physical change or chemical change or a nuclear change. Whatever change your matter undergoes, this is called the system. Okay, so it could either be a physical change or a chemical change or a nuclear change. When it undergoes those changes, it's either going to release or absorb heat. And when that happens, the heat is either going to be released to or absorbed from the surroundings. Okay, so the surroundings are basically whatever surrounds your system. So your system, if it was a physical change and it was water boiling in a pot, so the water boiling would be your system, and anything else would be the surroundings. The pot would be part of the surroundings, the air, the stove that it's sitting on, etc. You can have three different kinds of systems. So you can have an isolated system, which is like completely thermally isolated from the surroundings. Okay. And energy cannot get in. Okay. This is what this is showing here. Energy is not able to get into the system, and matter cannot get into the system either. You can have a closed system where you have a boundary or a barricade around the system itself. So it's contained. However, energy can come and go from the system. Matter could not. So think of a lid on a flask, an Erlenmeyer flask. So nothing can come or go, but heat could escape through the glass, for example. And then you can have an open system that the system is open to the surroundings. Matter can leave, it could come in, and energy could also be exchanged as well. One last concept to be aware of with energy is the law of conservation of energy. And this law states that energy can be converted to one form or another, but the total energy in our universe is constant. So we are not gaining energy over time, we're not losing energy over time. And because of that, we say that the energy of our universe is equal to zero, right? It doesn't have a value because it's constant. And we know now that everything in the universe is made up of the system itself, so the physical or chemical or nuclear change, plus the surroundings that surround the system. And if this energy of the universe is equal to zero, then we can rearrange this formula and bring the system to the opposite side of the equal sign. And we know that whatever the energy of our system is, that should also be equal to the energy of the surroundings, with just, again, either a negative sign applied. So if the energy of the system is releasing energy, then the surroundings is absorbing it, and vice versa. All chemical processes either release energy or absorb them. And so if the process absorbs energy, we call it an endothermic system. So endothermic right here is where energy flows from the surroundings to the system. This means that it absorbs energy. If it is exothermic, exo sounds like the word exit. So this is where energy flows from the system to the surroundings. Okay, so it flows out of the chemical process and into the surroundings. So take a look at these scenarios right here and consider whether these processes either absorb energy to have them happen or release energy. And call me over and I'd be happy to check your answers.